Hello and welcome back for another VMK. In this VMK, I'll show you how to create a rolling ball with the help of some Quaternion math. The source code that I'm starting off with comes from the Physics Engine series. So if you want to start off at the same spot that I'm starting off with the code that came after VMK 14b. So if you've completed this one, then you'll have all the code that you need for this VMK. However, it's not necessary to really have all that code, since I'm going to be talking about something a little bit different than what is explained in the physics series. What we have is a testing LVL file which looks like this. We have a grid, which is our ground, and we also have a sphere that's relatively smooth. It's 21 by 21 divisions in the H and V direction, and the sphere has a radius of 0.8. This number is important to remember because it'll show up inside of our code a little bit later on. I've applied a regular material to it, but also a texture to the sphere that has a pair of stripes on it so that we'll be able to see when the ball is rolling or not. And then here's our structure for our scene graph. We have just a transform with our shape for our grid, and then a nested transform named ball, which is what we're going to be controlling in this VMK. So let's take a look at the source code, and inside of the scene class, inside of the update function, I have a function call here, find node, to find the ball item. If we find it, this guy here should not be null, so we'll go inside of this if statement. And inside of here, what I'm doing is I have an acceleration value, which I've set to 2. This controls how quickly we can move the ball around on the screen. And the motion is controlled by the arrow keys. You can see here, if we press up, then I'm changing the Z value. If I press down, then I'm changing the Z value. The only difference here is the sign. And then if we're pressing left or right, then I'm changing the X value. And again, the only difference here is the sign as well. So the acceleration value is controlling how fast we're pushing against the ball, and the arrow keys are directing us in which direction. So this ends up being a vector pointed in the XZ direction. I then have a check here to see if the acceleration value is equal to 0. So the length of this vector, if he returns to us a 0, then we're going to go into here, and what we want to do is slow down the ball until it basically stops moving. I'll talk about this in a second, so just forget about this for now. If the acceleration is non-zero, meaning we are pressing some keys on the keyboard, then this is the standard Euler equations that we've seen earlier in the physics series, where I'm taking acceleration, multiplying it by the time factor to give us a velocity, and then I'm taking the velocity, multiplying by a time factor to get the position. If the position is changed, meaning it's non-zero, then I'm going to update the current ball's translation value by however much we've changed up here due to this calculation. So basically what we're going to see here is there's the ball on our screen. When I'm using the arrow keys, I can slide the ball around, and notice that basically I can press and hold the arrow, let go, and it kind of slides itself to a stop. The reason why it's sliding to a stop is because of this damping factor which I've implemented here. Basically when acceleration is 0, meaning I'm not pressing any keys, then I figure out the negative velocity, so the opposite direction in which the ball is currently moving in, normalize that so that I have a normal vector pointing in the opposite direction that it's moving. I apply a damping factor. This number here is arbitrary. The larger you make this number here, the faster it'll damp down to stop the motion. And the way that is calculated is damping factor times the velocity, which is the negative value here, times the time step, and then that's our new velocity that will slow down our ball until eventually it comes to a stop. So this is should be fairly familiar to you if you finish the physics VMKs up to VMK number 14. So now what I want to do is I want to not only be able to slide the ball around the way that it's moving right now, but I also want to be able to roll it so that it looks like the ball is rolling. I'm going to jump here into Photoshop to show how we're going to derive the equations to figure out how to roll the ball. I'm drawing this freehand, so it may not look like a sphere, but imagine that that's a perfect sphere which has a specific radius. We know what that is. And we've already calculated how far this ball is rolling. So let's say at time 0, we're located right here, and then at the next time step, we want to roll the ball to this location here at time 1. So we need to know how far we need to roll this ball to cause it to stop at this location here. So in other words, well, the way that I've drawn this is kind of hard to see. Let's say that at T1 we wanted to move it here, and T2 we're over here. What we want to do is we want to figure out how much do we have to rotate this ball to cause it to move to this location here. Well, since the ball is perfectly spherical and perfectly round, we know that it will make contact with the surface at all points in time. So in other words, this distance here, let's call it S, has to be some distance along the curvature of the sphere. And if this is the current location, then we are looking for where are we relative to the beginning point here so that this distance, this curved distance, is also equal to S. And if we draw some lines over here connecting everything up together like so, then this angle is basically what we're looking for, and that's what we need to apply inside of our equations. Well, there just happens to be a very nice equation between the relationship of this angle, this radius, and this S value, or the distance that we've rolled. And that equation is equal to S is equal to R theta, where theta is the angle in radians. So in other words, if we were to have a ball, let's say we wanted to roll it exactly 90 degrees, then we can see here that S is equal to R theta, and let's, for demonstration purposes here, say that R is equal to 1, then that means if R is equal to 1, theta is equal to 90 degrees, 90 degrees represented in radians is pi over 2, then this tells us that S, the distance that the ball has traveled, is equal to pi over 2, or about 1.57 units. Now what we're doing is a little bit different. We're basically saying, okay, we know this distance that we've traveled. What is the angle? So we can rewrite this equation so that we're solving for the angle where we're just taking S and dividing it by R. So that's why I said earlier we need to know what R is, because R plays a role in terms of our calculation for theta, which is what we need. All right, let's jump into the code. Now you may think that you'd want to implement this sort of thing as shown here, where we get the angle that is changed in radians by getting the position distance, this is the distance that we've traveled, and dividing it by the radius of our sphere, which I said earlier is 0.8, which we can see over here, 0.8. All right, so that's going to give us the angle. Then we need to rotate the sphere, so that means we need to get a rotation axis as well as specify the rotation angle. We have the angle already here. We just need to convert it to be in degrees, since that's what OpenGL uses. So we're passing in that angle change value in radians into our radians to degrees function, which will convert it to degrees. And then we're just taking that rotation angle that's currently stored there, initially is 0, and we're just going to add it to whatever the change value is. So that'll update the angle. But we also need to specify the rotation axis. And because we're working sort of in a pseudo 2D world, I mean, we're only rotating along the plane XZ, so that means that our rotation will be parallel to that axis and perpendicular in the direction that we're traveling. You've seen this already previously. I think I might have had in the math VMKs when I talked about perpendicular vectors, we can just swap the x and the z value and just stick a minus sign to give you the perpendicular vector if you're talking 2D. So over here, if we know that we have a 2D plane such as this, x and z, then if I were to draw some vector like this, v1, and it has value x, z for the direction, then a vector that's perfectly perpendicular to this one, let's call it v2, its coordinates would be basically equal to z minus x, like so. So that's exactly what we're doing here inside of the code. We're just flipping the x and z components and sticking a minus sign for the z value. So let's try this out and see what happens. I'm going to roll the ball to the left. Notice that it rolls very nicely, very smoothly. However, note what happens when I try now to roll the ball back in the right direction. There's a little jump and then it rolls smoothly again. So going to the left, there's a little jump, rolls smoothly. going to the right, little jump, rolls smoothly. That's not too bad. It doesn't look too bad, but now watch what happens when I try to roll in 3D. Notice the ball is rolling erratically, and sometimes it looks like it's almost spinning on the spot, like when I'm changing direction. So obviously there's something really wrong with the way that this is implemented, and it basically boils down to the way that we're deriving this rotation axis. Since it's always pointing in the opposite direction that we're traveling, we are going to get these discontinuities when we're changing directions. All of a sudden, you know, we're pointing in one direction, we have a specific angle and axis, but then when we jump into the opposite direction, the computer doesn't know how to smoothly interpolate from one angle location to another, so it causes that jump which you see on the screen. However, the rolling rotation looks half decent anyway. Well, there is a way to fix this, and there's really a better way to handle this rather than doing it the way that it's shown here. And the better way is to use Quaternion math. Quaternions are very helpful for solving any kinds of rotational problems in 3D. You'll notice that when you talk about Euler equations inside of 3D, people will talk about gimbal lock and causing singularities with your joints when you have rotating joints for animations and things like that. To get around those kinds of problems, it's always recommended to go to Quaternion math. Also, if you're interpolating angles over time, it's far easier to interpolate the equations using Quaternions rather than using Euler equations. That's another big reason to go to Quaternions. Now, I have this website here, which I highly recommend you guys look over if you're interested in figuring out what Quaternions are and how to use them. I'm only going to implement a few equations for this specific tutorial. There's a lot more equations you can implement in C++ to work with Quaternions if it's something you want to do. However, in this equation, I'm only going to need a few specific equations to do a couple calculations to make the ball roll properly. So the URL here is www.flipcode.com/document/matrfaq.html. There's a lot of good information on here that explains how Quaternions are represented in equations and how to perform mathematical operations using Quaternions. They're somewhat similar to vectors, but also they have a little bit of extra math involved in them. So let's take a look at the Quaternion equations that I'm going to implement here in C++. I'm going to replace this code with the following. We still need to know how far we're rotating in radians, so I still calculate that based on the radius of our sphere. But this time, what I'm going to do is generate two Quaternions. Q1 here, I'm generating by taking the current rotation angle of our node transform and also passing in the rotation axis. So these are the current values of the transform. The second Quaternion that I'm calculating here is a Quaternion based on the angle that we're going to be rotating, and we've seen this already. Here's the vector of the axis that we're rotating about, and here is the angle that we're rotating about. So these two Quaternions, Q1 and Q2, what I'm going to do is multiply them together. Now, when you multiply Quaternions, Q2 times Q1 is not going to equal Q1 times Q2. So the order in which you multiply these is very important. So I'm taking basically Q1, which is our current angle, and multiplying it by Q2, in other words, updating it by the angle change here. This is going to give us a new Quaternion value. I can then take that Quaternion value and convert it back into an angle and an axis, which I then apply to my node transform. So if I were to compile this and give it a run, we can then take a look to see how well it works. Okay, I'm turning to the left. Now, if I press on the right arrow key, notice it smoothly moves to the right. There is no more jumping in the calculations when the ball is moving. And I can move in any direction that I want, and it's always perfectly smooth, rotating the ball back, forward and back, left and right, and so on. So Quaternions are beautiful for this kind of calculations because there are no singularities that it experiences, and there is no jumping in terms of the angle that we're rotating about, as well as the axis that's used for the rotation. So the problem is solved quite well. All we need to do is see how to implement these Quaternion equations, or how to implement this Quaternion class more specifically. You see that I've created a constructor that accepts a angle as well as an axis. I've constructed a multiplication operation for the quaternions, and also a getAngleAxis function call, which will return to us the angle value as well as the axis, which we then apply to our transformation. So let's take a look at the Quaternion class now. Here's the definition of the Quaternion class. If not defined, Quaternion underscore h, define it, standard stuff. The quaternions are basically a collection of a floating point scalar number, which I call here fw, and a vector, so v3. This is comprised of three components, x, y, and z, and then we have this extra component, which is w. I have a standard constructor here, which takes in no parameters. I have this constructor here, which is the one that we're using in this example, and I have a destructor. I have a multiplication operator, which is used to multiply this quaternion with another one, and it's going to return to us a quaternion. And then we also have a magnitude function, which will return us the magnitude, normalize function, which will normalize the quaternion, and also the getAngleAxis function, which will return to us an angle as well as the axis that this quaternion represents. So that's basically all that there is inside of this class. Our multiplication operator here is calculated as follows. We have the resulting quaternion that has the w factor as well as the vector factor. The w is calculated by the current quaternion's w value multiplied by this quaternion's w value, and then you subtract the dot product between this vector dotted with this quaternion's vector component. The v3 vector component of the result is calculated by the current vector's value crossed with this quaternion's vector value, but then you also have to add this quaternion's vector value times my scaling factor, the current scaling factor, plus my vector value times this quaternion's w factor. And then I just return that result. This equation basically you'll be able to find in here. If I scroll through here, how do you multiply two quaternions together? Well, there you go. Here's the equation for the w part, and then here's the equation for the vector part. So that's the same equation that you see here. To get the magnitude of quaternion, it's the same thing as getting the magnitude of a four-dimensional vector. We take each component, square it, add them all together, and then we square root the result, and then that ends up being the magnitude. To normalize, we do basically the same thing you do with a four-dimensional vector. We first get the magnitude of our cells. We check to make sure that it's not equal to 0. If it is, then I'm just going to default the w factor to be 0, the vector to be 0 as well, and return. Otherwise, I take the magnitude, invert it, and then multiply by the inverse, or in other words, divide both the w and the vector components by the magnitude, and that's going to give us a normalized quaternion. The getAngleAxis function, you pass in an address to a floating point variable and an address to a vector 3, and then internally here we're going to return both of these values. First thing that I need to do is make sure that the quaternion is normalized, so that's why I normalize it here. And then if the w factor here is not equal to 1, then we go and do this. If it is equal to 1, then this value here is going to evaluate to 0. So then we know we basically have no angle, so we return 0, and the axis doesn't matter because we're not rotating about anything. So I default here the axis to be 1, 0, 0, but it could really be 0, 1, 0 or 0, 0, 1 or any other vector at all, since the angle is 0. If the w value is not equal to 1, or minus 1 for that matter, then we can calculate the angle based on this calculation here. We take 2 times the arc cos of w, convert that to degrees, and the axis is calculated by taking the vector component of the quaternion, dividing it by the square root of 1 minus w squared. Then we also have the constructor here to take a look at. First, take a look at the regular constructor, where all I'm going to do is I'm going to set the W value to 1, and the vector component is going to be zeros, but we don't need to define it since it gets defined inside of the constructor, so that's why this is commented out. The alternative way to construct a quaternion is you pass in an angle in degrees and the rotation axis, in which case we need to calculate the W and the vector component, and we can do that by taking the angle value here, converting it to radians, and multiplying it by 1/2, and then taking the cosine of that value. That will give us the W component. The vector component is the sine of that angle that we just calculated multiplied by the rotation axis that gets passed in here, but it has to be normalized. For the quaternions to work properly, you always have to work with a normalized vector representing the axis of rotation. And the destructor doesn't do anything, so it's blank. So that's all there is to it. There's a lot of other functions you can create, like how to zero a quaternion, how to add quaternions, subtract them, find the conjugate, how to scale quaternions, calculate the normals, how to inverse, how to do a unit inverse, things like that. But I didn't bother implementing them because I didn't need them for this specific demonstration. The equations to do all that are described here on this website, so if you are interested in implementing them, go ahead, implement all the code that you need to use in your own projects. So I hope this video was helpful. If you have any questions about this video, come down to www.maticknows.com, click on the forum section, and once I upload this video, inside of the OpenGL Tips and Tricks VMK series, you'll find a link here to this VMK so that you can post questions specific to the Quaternion VMK.